Hi guys, I wanted to share two more master level problems with you. And kind of a topic today will be data structures not because I was like specifically looking for problems that involved data structures, but just because I randomly stumbled upon two such problems. So that's kind of a topic for today. Keep that in mind. The first problem is 2200 problem. It comes from a Deltic summer round, so a quite recent one. In this problem, that's problem E, so not that easy, but also not like extremely hard and overcomplicated. In this problem, we have two arrays A and B, each of equal lengths. We will need to process several queries of the form left and right, which means that we want to equalize subarrays of A and B, both from index left to index right. And we want to equalize them with a sequence of like special operations where we select some position, let me draw it because that's just easier to explain. We have array A, we have array B, we have some subarrays from left to right. Want to equalize them, the operations we can perform is we select several positions in even number of positions, I believe. Like let's say we select this position, then somewhere here this position in A, this position in B. And what we do is, I believe we increment all of this, all of odd positions in A by one, like first, third, etc. We also increment like second, fourth, etc. positions in B by one. So these get incremented. And we want to equalize these subarrays within the minimum number of operations possible, or tell that that's impossible to equalize them no matter how hard we try. There are several samples, you can look through them if you want to. Assuming that you spent some time thinking about this problem, I will start going through my ideas for it and how I approach it just in general. First thing I noticed, like it's quite it's not very nice to deal with two arrays. Why? Like I want to equalize them. Equalizing means that I want difference to become zero. So I define it second, it's like third array diff, or d for short, such that di was just ai minus bi. And this way, like my intention will be to make d from left to right equal to zero array. And my operation changes from plus 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 to plus minus plus minus, or something like that. So, okay, getting rid of one array, like two arrays, getting only one array remaining, it's nice. Now we have to like come up with a way to quickly understand like how many operations we are going to spend on a given subarray to make it equal to zero. Now the first thing I noticed here is like, well, let's actually, before we delve into minimizing the number of operations, why don't we think about what cases lead to the impossible answer, and here I was thinking about, once again, to like re-promote the idea from yesterday. When you're faced with a construction and some operation going on this construction, you like almost always want to look for some invariants that your operations preserve. And in this case, that is obviously like whatever operation you perform, it does not change the sum of subarray. And therefore, if the sum of subarray is not 0, so let's say like dl sum going all the way up to d right, that is not equal to 0, then you can just bravely say like, okay, that's impossible, like no matter how hard we try. I have to quickly check if some subarray sum is non-zero. Well, I just used prefix sums. Then this thing becomes prefix sum at right plus 1 minus prefix sum at left not equal to 0. So you only spend like constant time to check if answer is 0, if is -1 or not, or like some finite number of operations can get you there. So that's kind of a like smallish special case, let's put it this way. But obviously, like mostly the problem will, the test cases will give us the cases where the sum is 0 and we have to do something with it to find the minimum number of operations. Here, for quite some time, as you can see on the right, I just got the wrong idea of what I want to do. Before we actually start realizing what we want to compute, it's kind of like you can realize a separate idea that is kind of orthogonal. So like what we actually want to compute is how we are going to compute it. And this kind of a situation when we want to like say something about pluses, minuses on a segment, it sounds a lot like we are going to need some data structure. The data structure I used in my implementation is a segment tree. Nothing crazy, no like lazy propagation, just regular segment tree. So I realized that it's likely that every query will going to take logarithmic time. I don't mind so much about that. Now I just have to figure out what the query should actually return for each subsegment. So initially I was thinking like, okay, let's take a look at some of these guys, some of the examples. Like, I already said that I'm considering a difference array. So why don't we just write it explicitly for the first sample? So difference array will, well, I mean the difference of two arrays, not the difference array. Difference of the arrays is something like that, I believe. So here I unfortunately got the wrong idea because like I was thinking like, okay, like you see these three guys here, right? I mean two guys with a sum of -3. All such operations, you can't have one operation that affects two of these guys because there is no minus in between them. We have to, like, we want to increment that by 1, that by 1, and that by 1. And what I'm saying is that these three increments belong to three different operations because you can't place a negative, like a minus between them, a decrement, because there is no place between them. So that was kind of my idea. I thought that I want to find the maximum group of numbers of the same sign, and that is possible with segment tree. But eventually, after spending quite some time getting the wrong answer on test 17, I realized that like it's not always possible that this kind of construction is it's possible to come up with that number of operations that will yield like a correct correct sequence of operations. So the tricky part here is, let's say we have not -1 here, but -2. So what I'm saying, like, okay, I may want to place this and this into the same operations, right? I don't want to use other operations because we already discussed our original intention is that this is minimum, right? This is minimum number of operations that we can achieve, and we can achieve that. So I have to put those two increments into some of these operations. But then you can realize that I have to place -1 in decrement between those pluses, decrement between those increments. And I kind of end up with a bad situation where this +1, it's kind of there, but it got more decrements than it should have. So after you realize this, you effectively realize that, well, I actually care not about consecutive sequence of numbers. So I care about maximum or minimum subarray sum. Alternatively, you care about maximum absolute value of subarray sum. Alright? Because you're surely going to need at least that many operations, because you need to perform that many different increments or decrements that you cannot chain together, because you already used all like other guys. Well, you got the idea. All like decrements that you could perform in this positive one. Then you just have to understand how to come up with a segment tree that answers this kind of queries. What is the maximum absolute subarray sum in some subarray? So, like, for example, we acquired this subarray. Let's say, to make things legal in a way, so that here we have -2, but here we have something like 4. So we are queried about this subarray. We should respond that this is the maximum subarray sum of -4, maximum absolute subarray sum of -4. We could also say that this one is maximum absolute sum with +4. Once again, like in more complicated cases, there needs not be one like consecutive subarray of numbers of the same sign. Just to clarify why we need to like consider subarrays not only of the same sign. So now we have to come up with a segment tree implementation that can answer such queries. And here it greatly helps to look at the implementation section of some generic segment tree. We'll show what I mean by that. So if we close that and just take a look at our implementation. Well, first of all, our main function will be like just, okay, reading input, computing difference of two arrays, computing prefix sums, and we build our segment tree, special case of subarray sum not being not 0. And we just query and answer, right? So this like is very generic. Segment tree class takes care of all the inner workings, how we combine segments, etc. And you will also notice that, to be fair, we also need one more special case. That is if you're like all samples had like negative something, then positive something that balance out. But if you have positive something and a negative something, that you can't get rid of that +2. So technically, we also need to check that maximum prefix is not positive, because then we can't get rid of this prefix. That's why I had run answer on test 81, because I forgot about this. But if you look at our segment tree class, you may expect like details of how we combine segments to come up here, but it turns out that they don't. And that's a cool thing about having a generic segment tree. And I was actually very proud of myself for writing it from memory, because I usually have to refer to like cpalgorithms.com implementation. But here I finally memorized that. So yeah, a little bit proud of myself on this one. Here, like you can see, these are like wrapper functions that go into this special kind of information where you carry like current vertex in each tree and what subarray it corresponds to. And your general scheme is like, sometimes you can answer immediately. Sometimes you have to divide tree segments into 2 tree subarrays, perform some operation on each of them, and then combine the results. And that's a cool part. Like that combine function, you may have noticed that our segment tree is a template of class T. We're not telling it what the T is, but all we're telling is that combine function takes 2 arguments of type T, like tree at somewhere, and returns another value of type T. And all inner workings, like problem-related, problem-specific inner workings of combine function, they are in the combined function for that type. So we like define a type tree node and write combined function for it. And that's it. Like our segment tree implementation needs not to change. Our main function usually needs not to change. Except for we may want to like get into the details of how tree node is implemented if we have some special cases. So that's a cool part. Like this is not going to change. It's not going to change. Like no matter which type I want to store in my segment tree, I just have to write custom combine. Now that should be possible to have combine function is, I think like you can make more template arguments to this to make it even better, but that's like the level that I'm currently using it on. So our tree node turns out it's enough to store 5 integers for each subarray. Maybe it's possible to store even less, but like who cares? Less data. So what I store is like minimum prefix, minimum suffix, maximum prefix, maximum suffix, and sum of the entire segment. Which I could have actually used to answer, like, to get rid of prefix sum, but whatever. Why is that? Because if you remember cadence algorithm, to find maximum sum subarray, it cares about maximum prefix, maximum suffixes. Rather, it cares about maximum prefix and minimum prefix so that it can subtract them. I have somewhat a similar idea, so this part is just like constructing this tree node structure from like 1 element or from all 5 elements. And also it has a method value that will like just combine. Because we don't care if it gets negative or positive values, we don't care like which one of them is before which one. So we can just subtract like that, subtract like that. Both of these values are already positive, so we can just take maximum without caring about absolute value too much. Depending on which occurs first, maximum prefix or minimum prefix, like if minimum prefix occurs before maximum prefix, then you should actually subtract the other way around, and you will get a segment of negative. No. Let me make it clearer. So if there is a minimum prefix and then maximum, and it means that you increased from somewhere to somewhere. So you're actually getting like positive subarray. If, however, you have minimum after you had maximum, it likely means that you decreased from there to here, but you don't care because you want maximum absolute value of some subarray. So that's like the slight difference from cadence algorithm. And we have a combined function, like what is the minimum prefix if you consider two guys together? Well, it's either the prefix of left or entirety of left plus minimum prefix of right. This kind of thing carries on for all four of them, and then sum is just sum of two guys. Like it turned out quite easy. If you have a segment tree template, or if you can write it from scratch reasonably quickly, which I believe at this point I actually can stop using my segment tree template and just write it from scratch. Previously I was using a template because I could not just remember all middle plus one, maximum minimum, stuff like this. But luckily enough, now I remember things. So I may like just have a compact version of that template that I can type. For example, if I want to participate in some offline competitions where you can't use your library. That's quite nice to have. So yeah. The link to this submission, as always, is in the description of this video. So if you want to get your hands on this template, you're welcome. But we will take a look at the second problem of today. It comes from a Harbor Space Scholarship contest. That is problem F, and it's 2300 rated, which mostly, unfortunately, that comes from implementation difficulty, not from the problem difficulty itself. Because the problem is quite short. It gives you an array and it wants you to find some values of like some sum for each prefix of this array. Now, if you try to look at this, like it's for the first time you see something like sum of something modulo, you'll likely say, okay, I'm pissing out of this contest. I don't really want to compute like sums. I'm not a calculator, right? Like that sounds like a task for a calculator. No, thank you. Like I'm not gonna do that. However, if it's not your first encounter with such a problem, you're likely to realize that, well, that modulo is kind of annoying, and also like the thing that AI and AJ are not ordered is also somewhat annoying, but surely we can work through it. Like we just need to be ready to suffer a little bit, and we'll work our way through it. So the first thing you notice is, of course, pk and pk plus 1 are very related to each other. Like pk plus 1 is pk, and then plus something, plus two sums actually. Well, actually plus 1, but we'll immediately split it into two sums because that is just the way it's meant to be. Here we have sum from I goes to 1 all the way up to k, ai modulo a k. Let me actually say that this goes here and this goes here. Alright, so pk is pk minus 1 plus the sum from I to 1, sum of from I from 1 to... That's confusing. How do you pronounce such sums? Okay. Let's not care about it. You can say the sum plural, right? So I don't need to pronounce every formula I write down. Assuming that may actually be more annoying than if I just write it down. The other sum is like, you have two options. Either you take AI modulo AK, or you take AK modulo AI. Now in general, if like numbers are arbitrary, there is nothing good to touch sums. I don't really know what we can do about it. But then you notice that AI is up, is reasonably small, up to 3 times 10 to the fifth. And also they are distinct. So you start thinking, okay. Like, there is something here. There is something, some hope. Why there is some hope? Because such sums, they are not, they like, of course, modulo is annoying, but once we get rid of this modulo, that will be more or less like understandable how to deal with them. And the way we get rid of the modulo is like very standard. We talked about it the other day. I'm not exactly sure in which episodes, but like, what is the remainder when you divide x over y? That is, start with x, you subtract several times value of y, and how many times? Well, x over y rounded down. Excuse me. I'm not exactly sure what that's all about. I don't remember myself being allergic to something, but whatever. So that's something like this, alright? And the kind of like the trick here is, of course, like you're faced with a terrible sum. If you write it down, well, you may see that, well, let's work through them for some time, but then I'll leave it for you to think about it for some time. So like this sum, let me box it in. This sum will be that minus what? Minus AK times AI over AK rounded down. You can get take that out. That will be just prefix sum. Alright, so nothing smart here. Negative sign, also don't care that much about it. So what we actually care about, like, it's how to compute such an expression, right? Because obviously we can't just let it be this way, because that's still all of k time per operation, and we kind of expect it to be quicker. I say log of something. Let's not say log of n. Let's say log of something. So actually we can also take AK out of the sum, because like we just want to know what this sum is, and we can multiply it by AK. If you've seen the other video, this I think even this week, we talked about it, like how do we compute such sums? Well, we usually want to group elements by something. It appears to me that here we want to group elements by what is like what is the ratio, because like many numbers will have the same integer part when divided by something, right? Approximately AK numbers. Because AK are distinct numbers, on average they will be like n over 2 at least. So what we can do, like we want some data structure once again that can tell us how many values of I there are, such that AI divided over AK is equal to J for some value of J. Then we'll all like we are able to loop over all values of g naively, of course, because how many values of j we are actually interested in? We're not interested in anything that's more than m over ak, where m is the maximum value in array A, right? So we know that j is at most this. And then when you average over all ak's, you see, okay, so I'm getting like m over a1 plus m over a2, etc., plus m over an different queries. And that number is not particularly large because like these numbers, the minimum they can get is 1 through n because they are all distinct. Like every word matters in the description of the problem. Now that sum is of course m log n, because that's harmonic sum multiplied by m. So all in all, what we arrived at is that assuming that we can make such queries quickly, there are not too many of them, so we can just do all of them. How to make such numbers quickly? How to count how many values of I fit in some range. And that is actually a range. If you look at it carefully, that is ak times j is at most ai, and ai is less than ak times j plus 1. That's just a range query. Any range data structure can answer those, for example, Fenwick tree, because that's like lightweight. I was a little bit worried about the fact that we like Fenwick tree will answer such query in log m time. And we have m times log n queries, so overall that's a little bit worrying. But then I noticed the time limit is increased, so I was thinking like, okay, it may end up being tight, but it should be fine to have two logarithms. But I did not want to have a segment tree because segment tree is more like Fenwick tree is essentially a half of segment tree. Like if you think about it carefully, they only store left children of each vertex. So yeah. But if we compare memory usage, like usual implementation of segment tree requires 4 times the memory, so I just really wanted to have like a lightweight solution for this one because I was a little bit worried about two logarithms. So I went with Fenwick tree. Fenwick tree, of course, can have range queries and pointed dates, nothing special here. So like we kind of dealt with this sum. Once you do it, take a look at this, and well, like it's more or less the same thing, more or less. So now let's take a look at this thing. We already said like that have to get rid of the modulo. So let's just do it carefully once again. It will be ak minus ai times ak over ai. Once again, you can get rid of ak because that is just ak counted k times or k minus 1 times, depending on which order you perform the operations in. And you can get rid of negative sign because that is just like okay, like you can apply it after calculating the sum. Here you have to think about like what are we going to do about it. Naturally, once again like this time the problem is that you are counting like the different part, you counting the denominator of ai. And well, that is not that easy. But if you think for a little bit, like you still want to group by something. So like when you come to AK, you want to know what that value is. So what I was thinking like, okay, so it appears to me that this kind of sum is in a way dual to what we have had before. So maybe we are going to need range updates and point queries, because we are effectively going to query some info related to AK only. And what updates can we carry out? Like, once again, AI contributes AI times J to all intervals such that AI times J here is at must AK, and AK is no greater than AI times J plus 1. So what we effectively have is we want to add AI times J to such intervals. And that's all we want. So we want range updates, and then we have point queries for AK. It's very convenient to think about this kind of thing that, well, as a black box, like I can do range operations and point operations as long as they are dual with a Fenwick tree. It's very lightweight. And then you just have to like understand, well, how to compute sums quickly. Very general idea that comes over and over again. If you're computing sums that involve integer part of some division, you want to group it by something. Usually you are able to do that because numbers are not large, and therefore the possible values of this sum, there are not too many. Once again, like here, maximum value of J will be M over AI. Maybe plus 1, whatever, like something around here. Because that is like just how many different values you have, how many updates you want to process. That's just that. So actually I realized this idea kind of quickly, and it was like, because that is just like very common ideas how you can compute such terrific sums. You want to get rid of the modulo, and you want to group by the value of like integer part of the division. So yeah. But then on the implementation side, it was a little bit annoying because I needed two different Fenwick trees. One for range updates and point queries, and the other one for range queries and point updates. Of course, Fenwick tree can handle both, but like you need two different Fenwick trees for that. So I'm going to show you the implementation that actually uses sum notation for these sums. That I'll honestly a little bit looked up the notation in the editorial. Okay, that was just much clearer this way. So S is the first sum. No, S is... Check. Let me check. S is the second sum and T is the first sum, actually. We have two Fenwick trees, again generic templates. They use one-based indexing because that is just a cool trick of having these bit operations dual to each other. Once again, link to this submission is in the description, so if you want to get your hands on the template of Fenwick tree, that I don't consider to be the most beautiful, but like whatever. And you can do that. This one is range queries point updates, as you could have guessed, and this one is range update point queries. That's also transparent when you look at the public interface of such classes. So what I need, I said previously that I'm concerned with like how many updates I'm having, so I just take maximum elements, and then I will process updates such that this is at most this in both cases. So as second sum updates with the current element times like how many elements it pairs with. First sum updates with the prefix sum, we already talked about that. And second sum cares about point queries. First sum cares about range queries. This is like j times ak, and then minimum of, well, like technically you want this, but then you have to, like, this Fenwick tree does not really work well if you supply indices that are bigger than the size, so you have to unfortunately take care of that yourself. Like, you don't supply size too large, because you may end up hitting some not initialized memory, getting some values without having runtime error. This is like undefined, typical C++ undefined behavior. So we make queries on such segments in both cases, so that is actually not very annoying. And here we have this little thing that it's like a range update. We take AI into the update because there will be no way to process it afterwards, so that's like another thing you have to take care of. But yeah, but overall, these lines, they just resemble the algebraic manipulations that we carried on over our sums previously. That should not be, that is a little bit like annoying to come up with all little indices and details to make sure they're right. But often there is not much thinking to it, they're just being careful, taking care. And the sum is first sum plus second sum, nothing strange. And we actually also need to update prefix sum, but like whatever, that's little details. So yeah, that's what I wanted to share with you today. I find it interesting how like we had two data structures in one day, data structure problems in one day. The way I encourage you to think about such data structure problems is the way that I believe Galen Collin has a very nice like meta on it, that you want to think about the data structure as a black box that supports some operations like efficiently. So you want to think about your problem in terms of what operations I want to perform, and then choose an appropriate data structure for that. So like, the first problem, I realized that I want to have like a lot going on in my segments, so I probably want something like a segment tree. And in the second problem, I realized that I want something lightweight that can do only two operations, like point update range queries or range queries point updates. I don't need range updates and range queries, so it's not really necessary to have a segment tree. And I also wanted something lightweight, so I picked Fenwick tree, a pair of them, because why not? And another recurring idea that we've seen in this like modular problem is when you're faced with modulo, you mostly want to get rid of it immediately. When you're faced with integer part of the division, you want to, with some of such things, you want to group them by something. And it's just a matter of like coming up with a good grouping method. But usually there's like a limited number of options that you have, and one of them works and others clearly don't work. So yeah, that's why like these problems are still master level and not grandmaster. They don't require you to come up with something you have never seen before. That is just like that is still like common tricks, to be fair, to be honest. It's just a matter of like how much time you spend on it, working through different problems, and therefore how many different tricks you know. But I believe that those tricks are kind of easy to understand and remember. So that's why I wanted to share such problems with you, because like you may actually end up using Fenwick tree in like lower rated problems as well. Yeah, some people even use segment tree. I'm not a big fan of overkilling problems with segment tree, but sometimes it is the right choice. So yeah, that's all I wanted to share with you today, guys. I hope you learned something new. I hope you kind of get into the shape of into the set of mind of thinking about problems in terms of common tricks that they involve. For me, this approach is highly beneficial because I think that these tricks, they represent they are a good abstraction. And I like to think about problems in an abstract way, in a way okay, what I generally want to achieve in this problem, what is slow, what I want to optimize. It's some range operation. Well, I need a range data structure. I need to get rid of annoying sum. Well, I have to group that sum by some value, right? It's generic ideas and principles that apply very often the higher you go. But they are not hard, so that's why I find it useful to share them with you. So once again, that's it for me for today. I hope you learned something new. And I'll see you tomorrow with a Grandmaster level problem. I'm still debating on which one it's going to be, because one of them is just very hard, in my opinion. I don't know why it's only 2400 rated, but okay. So maybe I will pick a new one. I already solved this one, but maybe I will pick a new one that is more educational in a way. So yeah, bye bye guys.